Hello everyone, my name is Dr. Raj Dandekar. I graduated with a PhD in machine learning from MIT in 2022 and I am the creator of the Build DeepSeek from Scratch series. Before we get started, I want to introduce all of you to our sponsor and our partner for this series, invideoAI. All of you know how much we value foundational content, building AI models from the nuts and bolts. InVideo AI follows a very similar principle and philosophy to that of us. Let me show you how. So here's the website of InVideo AI. With a small engineering team, they have built an incredible product in which you can create high quality AI videos from just text prompts. So as you can see here, I've mentioned a text prompt, create a hyper realistic video commercial of a premium luxury watch and make it cinematic. With that, I click on generate a video. Within some time, I am presented with this incredible video, which is highly realistic. What fascinates me about this video is its attention to detail. Look at this. The quality and the texture is just incredible. And all of this has been created from a single text prompt. That's the power of NVIDIA's product. The backbone behind the awesome video which you just saw is NVIDIA AI's video creation pipeline, in which they are rethinking video generation and editing from the first principles. To experiment and tinker with foundational models, they have one of the largest clusters of H100s and H200s in India and are also experimenting with B200s. NVIDIA AI is the fastest growing AI startup in India, building for the world. And that's why I resonate with them so much. The good news is that they have multiple job openings at the moment. You can join their amazing team. I am posting more details in the description below. Hello, everyone, and welcome to this lecture in the Build DeepSeek from Scratch series. Today, we are going to learn how DeepSeek V3 and DeepSeek R1 actually implemented an advanced version of multi-head latent attention in which they integrated multi-head latent attention or MLA with rotary positional encodings. In the previous lectures, we have studied about latent attention and we have also studied about rotary positional encodings. So in this lecture, I am going to assume that you are aware of these two concepts. If you have not seen the lectures corresponding to these two concepts, please go back and revise these lectures because they'll be needed in today's lecture. So let's get started. If you take a look at DeepSeek version 2, so DeepSeek V2 paper, and if you scroll down below, they have a section on architecture in which they start explaining about latent attention. In section 2.1.2, they mention something which is called low rank key value joint compression. And this is the basic version of multi-head latent attention which we have seen in one of the previous lectures. This is the basic MLA schematic. So let me just write it down over here. This is the basic MLA. Okay. Now, this is not the actual latent attention mechanism which they used to train their version 3 and even the DeepSeek R1 model, which became so popular in 2025. So, in the same DeepSeek version 2 paper, they have a section called 2.1.3, which is called as decoupled rotary position embedding. Here is where they actually explain how they adapted the latent attention mechanism to include rotary position embedding. And they have shown a bunch of formulas over here. So this is in DeepSeek version 2 paper. If you go to DeepSeek version 3, they directly explain the multi-head latent attention with rotary positional encoding. They don't explain the two types. They don't even explain the basic version. They directly start with the advanced version. So if you start reading the DeepSeek V3 paper directly, it's very difficult to understand these formulas, right? There is formula number 1, 2, 3, 4, 5. There are so many symbols over here. There are so many dimensions, and it's really impossible to figure out what exactly is going on. So many blog posts and so many articles which I have seen directly start with these formula, which are very difficult to understand. There are many dimensions to unpack over here, and so it is my aim in this lecture to explain you the nuts and bolts of what exactly happens behind these formula, so that when you go back and read the paper again, it will be so much more easier for you to understand. So let's get started with today's lecture. Okay, first I want to come back to why do we need to adapt the latent attention mechanism to include rotary positional encodings. So let's start the lecture with that. And to understand that, we have to understand why latent attention actually works. So if you see this schematic, which you have seen earlier, in latent attention, the input embedding is multiplied by this WDKV matrix, which projects my input vectors into a latent dimension. And in latent attention, in multi-head latent attention, we only need to cache this latent matrix. And the reason this caching works is because latent attention implements something which is called as an absorption trick. So if you calculate the attention scores, it will be queries multiplied by the keys transpose. So queries can be represented as x times WQ, which is the trainable weight matrix, and keys can be represented as if you see over here, the keys are CKV multiplied by WUK. So the keys can be represented, the keys transpose is WUK transpose multiplied by WDKV transpose multiplied by X transpose. So the main thing which I want you to focus here is that in the latent attention mechanism, these two matrices are absorbed into one single matrix. So WQ into WUK transpose becomes one single matrix. And then what remains is X times WDKV transpose, and only this needs to be cached. This is called as the absorption trick. Whenever a new query comes in, it's multiplied with WQ and also WUK transpose. Both of these matrices are fixed at training time, so we don't need to cache them or compute them again. The only thing which needs to be cached is the latent matrix of the inputs. So this is the main thing which you need to understand in latent attention and why it really works. If you have not gone through the multi-head latent attention mechanism, please go through that, because there we cover this absorption trick in a lot of detail. So for the latent attention to work, we need this WQ and WUK transpose to be together so that they can be multiplied and absorbed into one matrix. Keep that in mind. Now imagine that we want to add rotary positional encodings to my queries and my keys. So let's say I want to do the exact same absorption trick in latent attention, but I want my queries to be added, or I want my queries to be injected with rotary positional encodings. So I'm calling this RPOS, which is rotary positional, and this is my queries X times WQ. And I also want my keys to be injected with rotary positional encodings. So the keys matrix, which is this, I apply rotary positional encoding. So let me just brush up your understanding of what exactly happens in a rotary positional encoding. Let's say we are looking at one particular queries or the keys vector at a given position. We divide that into groups of two, and then each group of two is rotated to form another vector. So for example, here we have two groups x1 x2 and x3 x4, and this is the first position, or this is the first query vector. What happens is this x1 x2 which was my original vector here, is rotated to form x1 dash x2 dash. Then x3 x4, which was my original vector, is rotated to form x3 dash x4 dash. And so if my original query values were, or my original query vector was x1 x2 x3 x4, now when we apply rotary positional encoding, it becomes x1 dash x2 dash x3 dash x4 dash. So if you apply rope to x1 x2 x3 and x4, it becomes x1 dash x2 dash x3 dash and x4 dash. So whenever I'm going to use this rope operation, or rope operation in my description later on over here, so when I use rpos, this is same as the rope operation which I showed above. So when I use rpos or rope, this is what's going to happen, right? We take in the full vector, we divide it into bunch of We divide it into bunch of twos and then we rotate each vector based on its index. So the key thing to understand here is that this transformation from x1, x2, x3, x4 to x1 dash, x2 dash, x3 dash, and x4 dash is dependent on the position, is dependent on the position of my query vector, because the rotations which will happen for this x1 and x2 will be different from the rotations which happen for these two, because these two are at different positions. That's one of the key things to understand, right? So this rpos function is dependent on the position of the vector. It's position dependent. This is the second understanding. The first understanding in today's lecture is that we need WQ and WUK transpose to be absorbed. Second understanding is that whenever I'm showing R pos here, it means that we take this vector, we break it down into chunks of two, and then we rotate every chunk. And the amount of rotations for every query vector and every key vector depend on its position. So this R pos is position dependent. The main issue which happens now is that, let's say, um, l- let's say now instead of multiplying directly xwq multiplied by this whole, you are now multiplying rpos of x, rpos applied to xwq multiplied by the rotation applied to all of this. The main problem which happens if you try to use the original version of the latent attention is now this wq and wuk transpose cannot be absorbed. Why cannot they be absorbed? Because there is another rotary positional encoding function which lies in the middle. And this rotary positional encoding function is position dependent. So we cannot directly absorb WUK multiplied by WUK transpose, because this RPOS changes according to which position we are looking at. So these two matrices cannot directly be absorbed. And that is one of the main issues of directly using latent attention with rotary positional encodings. If WQ and WUK transpose cannot be absorbed, it defeats the purpose of latent attention. Another issue which happens is that if these two cannot be absorbed, then it means that we need to recompute the keys for all the tokens during inference. The advantage which we got before was that we did not need to recompute the keys, right? Because this WUK was already absorbed into WQ, and what remained was the latent KV cache, which I'm already caching. So I don't need to recompute my keys separately. But here the issue is that since the RPOS or the rope rotary positional encoding which you are applying depends on the position, we need to compute the keys matrix, recompute the keys for all of my tokens during inference, because this RPOS depends on my token position. I cannot simply absorb WQ and WUK transpose. I need to recompute these keys during inference, and that will significantly hinder my inference efficiency. In fact, it defeats the purpose of latent attention. The main advantage comes from my absorption trick, WQ and WUK being absorbed together. Now that cannot be done, so I'll need to recompute my keys matrix for all the tokens during inference. That increases my inference costs and that significantly restricts my inference efficiency. So if you look at the a DeepSeek paper, if you look at the DeepSeek version 2, what they have written over here is that rotary positional encoding is incompatible with key value compression. To be specific, rotary positional encoding is position sensitive for both keys and queries. If we apply rotary positional encodings, WUK cannot be absorbed into WQ anymore during inference. So this sentence, WUK cannot be absorbed anymore into WQ, essentially refers to this part. WQ and WUK cannot be absorbed, right? Uh, and and this is because a rope matrix will lie between WQ and WUK, as we have shown over here. This RPOS lies between WQ and WUK, so they cannot be absorbed into one matrix. And as a result, we must compute the keys for all the tokens during inference, which significantly hinder the inference efficiency. That's the main problem. So we cannot directly use the latent attention which you earlier saw if we want to use rotary positional encoding. And why do we want to use rotary positional encoding? Because as we have seen before, rotary positional encoding gives us a lot of advantages compared to sinusoidal positional encoding. In rotary positional encoding, we don't add anything to the token embeddings. We don't contaminate the semantic information given by the token embedding. We operate at the query and the key level, which is much better. So here's the problem which is faced, right? The problem is that I want to use my latent attention mechanism, which is so powerful, but at the same time I want to integrate rotary positional encoding also into my queries and the keys. So I want my absorption trick to still remain relevant. So what do I do in this case? How do I get both of these objectives to be attained? What are the two objectives? I want to use my absorption trick and I want to include rotary positional encoding. How do I make both of these things to be possible? And the solution which DeepSeek came up with is actually pretty simple and straightforward. It's called as decoupled rope. So decoupled rope, if you take a look at the formula over here, it does seem very complex and it's very difficult to actually understand what's really going on here. And if you also take a look at the schematic which they have, so they actually propose a schematic. And if you take a look at this schematic also looks quite complex. There are so many symbols here. There is this KT, apply rope, latent. It's difficult to understand what's going on. But the trick is actually pretty simple. What DeepSeek said is that, all right, if I cannot absorb my WQ and WUK transpose with rotary positional encodings, why don't I simply break down my latent attention into two parts? So, for example, let's say we are going to come to attention scores eventually, right? We are going to do queries multiplied by the keys transpose. So, let's say I compute two set of queries and I compute two sets of keys. The first is QC, QR, which are the two sets of queries, and the second set of keys and the two sets of keys are KC and KR. What is this QC and QR? QC is basically my original version of latent attention without any rope applied to the queries. So this is without any rope or rotary positional encoding applied. That's it. And this QR, this is where I will come up with new vectors. I will create a new query matrix and I will add rotary positional encodings to only that query matrix. So if you think about it, now my total query matrix, which is over here, is composed of two query matrices. One query matrix is where rotary positional encoding is not applied, that is QC, and one query matrix where rotary positional is applied, that is QR. Similarly, KC is my keys matrix where rotary positional encoding is not applied, and KR is my keys matrix where rotary positional encoding is applied. So now my Q is the concatenation of these two and my K is the concatenation of these two, right? So if I'm going to take a dot product of queries multiplied by keys transpose, this can also be written as QC multiplied by KC transpose and QR multiplied by KR transpose. So now if you see QC multiplied by KC transpose, here we are not using rotary positional encodings at all, right? So the absorption trick will hold for this. The absorption trick will still work. So the main aim of multi-head latent attention, which we started with, which is achieved through the absorption trick, that still works here because rotary positional encoding is not applied. And in this case, the absorption trick will not work, and that's fine for me. I'll do those extra computations. So I'll do some amount of extra computations, and I will not use the absorption trick over here. But at least the absorption trick is used for a part of my attention scores calculation. So this is the trade-off which we make. We increase the number of computations by adding these QR and KR matrix. We add new matrices where rope is applied, and those are new computations for us. That's fine. But we retain the old magic. So let me write here. We retain the old magic of MLA on QC and KC because here the rotary positional encoding is not applied. So the absorption trick does work here. And it sounds like cheating, right? You cannot figure out how to do something so you just break it into two parts. One first part you don't do rotary positional encoding, one second part you do rotary positional encoding, and you figure out a way to bring these two together. So in the rest of the lecture now I am going to explain how decoupled rope actually looks like. But until now, I wanted to give you an intuition of what DeepSeek did. And I hope now you understand why it is called as decoupled. The reason it's called as decoupled rotary positional encoding is that we have one part which does not have rotary positional encoding at all. So we decouple rotary positional encoding from my original latent attention mechanism. Okay, so now we are going to see the practical implementation of how um, decoupled rotary positional encoding works. What are the matrices which are involved? In particular, we are going to go through all of these steps: 1, 2, 3, 4, 5, 6, 7, 8, 9. We are going to go through all of these steps of matrix multiplication on a whiteboard so that you can completely visualize it. So let's get started with that part. All right. So for now, what I want you to do is just forget about these mathematical formulae and let's just focus on what is written on the whiteboard. And later we'll come back and check whether it makes sense with all those formulas which are given, right? So the what I've done here is that I've provided a visual schematic of how um, the decoupled rope works, and you can see that I've split it into two parts, right? There is a part on the left. There is this. Let me actually do this with the black ink. There is a part on the left which is part number one, and there is a part on the right which is part number two. So part number one, which I'm going to show here, is no rotary positional encoding, and part number two, which is on the right, that is where the rotary positional encoding part is done. So that's why it's decoupled. It's very easy to explain this in two sections because both of these sections work separately. So what I'm going to do, I'm going to zoom in on the left hand side for now and just forget about the right hand side completely. On the left hand side, what I'm going to do is that I'm not going to apply rotary positional encoding at all. We are going to proceed just like we did in the original latent attention with small changes, which I'll explain to you. Okay, so let's get started. The tokens which we have is the next day is, let's say we have four tokens. The first thing which we have to decide is the number of dimensions, and that is denoted as D in the main DeepSeek paper. In this case, my D is equal to 8. Good, great. So we have four tokens, each with dimensions of 8. The second thing which we have to decide here is my number of attention heads. So NH is equal to 2 and my DH is equal to 4, right? So NH is essentially number of attention heads and DH is the dimension corresponding to each head, that will be equal to 4. So the first step which I do is that I take my input embedding matrix and I have to project it into the latent space. So we multiply it with the WDKV matrix. And the second dimension here is very important because that's my latent dimension. This dimension actually determines the size of my KV cache, my latent KV cache, and it's denoted by DC in the DeepSeek paper. So I'm just assuming this value to be equal to 4 over here. So if you take the 4 by 8 matrix and if you multiply it with a 8 by 4 matrix, you get a matrix which is denoted as CKV in the original DeepSeek paper. This is the one which I've shown with a black dotted box because this matrix is the latent KV matrix which is cached eventually. Only this is cached. This is my 4 by 4 matrix and the number of columns here is equal to DC and the number of rows is equal to the number of tokens. Okay. Then what I do is that I'll multiply it with two matrices WUK and WUV. That will give me my keys matrix, which is KC, and that will give me my values matrix, which is VC. Remember the dimensions of the keys and the values matrix are D, which is the original dimension which we started with. And the dimensions of WUK and WUV are DC, comma D. Okay. So this is how we get KC and VC. So this is just one part of what I'm showing on the left hand side where we get the keys and the values. But there is a second part in which we get the queries. And this is where there is one small change with respect to what we saw earlier. Earlier, what we saw is that we just take the by earlier, I mean in the previous lecture, we just take the input embedding matrix and we multiply it with WQ. That's what we saw earlier, right? We take the input embedding matrix and we multiply it with WQ. But actually in DeepSeek, what they did is they took the input embedding matrix and then they down projected it into a lower dimension. The matrix which they used to do that is called as WDQ and its dimension which they denoted was DC dash. Now, for the sake of simplicity, DC dash I'm assuming to be same as DC, which is equal to 4. But DC dash is another lower dimension where the queries matrix are projected into a lower dimension. So when my inputs embedding matrix is multiplied with WDQ, I get a matrix which is called as CQ. That is the queries matrix in the lower dimensional space. And this will be a 4 by 4 matrix. And then we take these lower dimensional query vector CQ and then we up project it back into the input dimension. So WUQ up projects my CQ back into the dimension D. So its dimensions are 4 by 8. So when CQ is multiplied with WUQ, that gives me my QC, whose dimensions are 4 by 8. So on the left hand side, the final three matrices which we have are KC, VC, and QC. Queries, keys, and the values where rotary positional encodings are not applied. This is the same schematic which we saw in the latent attention done in the earlier lecture. The only difference here, or the only difference in our current lecture, is instead of directly multiplying it with WQ, what we are currently doing is that we down project it to get this CQ matrix, and then we up project it again to get my ultimately to get my QC. And why is this down projection and up projection done? So DeepSeek, they mention in their paper that this saves the activation memory during the training time. So it turns out that down projecting the queries matrix into a smaller matrix reduces the activation memory or memory requirements during training time, and it also seems to lead to a better performance. So there are two additional matrices, WDQ and WUQ. Okay, and this gives me my KC, VC, and QC. Rotary positional encoding is not applied here. That's part number one on the left hand side. And now we come to part number two on the right hand side of my illustration here. This is where we are going to add new matrices. By adding new matrices, what I mean is that I want to take my same input embedding matrix and I want to construct new queries and the keys. Why do I want to construct new queries and the keys? Because I want to construct this QR, I want to construct QR and KR, because I will ultimately apply rotary positional encoding to those matrices, right? So first let me show you how the keys is constructed. So you take the input embedding matrix and you multiply it with a matrix which is called as WKR. So take a look at WKR very closely. The number of rows of WKR is equal to 8, because that's the same as my dimensions over here. But take a look at the number of columns of WKR. The columns of WKR are DHR. What are DHR? Remember, I am creating new matrices, right? So I want to decide the dimensions in which these new vectors will lie. And if I have two heads, so NH is equal to 2, right? DHR is going to be the dimension of each head in this new space where I'm going to apply rotary positional encoding. So for example, the ultimately the KR and the QR which I have, they will have a dimension of NH into DHR. So both QR and KR will ultimately have the dimensions of NH into DHR. So I want these new matrices to have these dimensions where DHR is the dimensions of each head in my new space where I'm going to apply rotary positional encoding, and NH is the number of attention heads. So here what we are actually doing is that WKR has dimensions equal to DHR. So we are actually going to share the same uh, trainable keys matrix WKR across all the heads. So that's why it has the dimension of DHR and not NH into DHR. If we are using different WKR for different heads, the dimensions of WKR would actually have been NH into DHR. But I'm using only DHR over here. And the key thing to understand here is DeepSeek also mention over here, they have a shared key across all the heads which carry the rotary positional embedding component. So that's what I'm illustrating here. The dimensions of WKR are DHR and not the attention heads into DHR. We are going to use the same weights across all the heads only for the keys, right? So we take the input embedding matrix, which is actually 4 by 8, and you multiply it with WKR, and that gives you a 4 by 4 matrix, correct? You apply rotary positional encoding to this 4 by 4 matrix. So this is where rotary positional encoding is applied. And remember, rotary positional encoding preserves my dimension. So after applying rotary positional encoding, I get a matrix which is 4 by 4, right? But this has only dimensions equal to 4. That is not good. I want to extend it across all my heads, right? So then what we do is we take this same matrix and we extend it across two heads. So I copy it across the two heads which I have, and that will ultimately give me the dimensions of 4 comma 8, and that is my kr. So remember I told you kr will be of a dimensions of number of attention heads into dhr. So now it becomes of the number of dimensions 8, which is dhr into nh. So what we do is that we actually use the same wkr across all the heads, as is written over here. The same key is shared across all the heads. So we use the same wkr, and this is and then we apply rope, and then this same key matrix is shared across all my heads. So we actually repeat this across two heads, and ultimately we get the kr matrix, which is 4 by 8. The way kr is different from kc is that the dimensions. So here kc has the dimension equal to d, and kr has dimensions equal to dh. Kr has the dimension equal to dhr into nh, which here I have chosen to be equal to 8, but it can be even different than 8 if needed. Another difference here is that wuk actually is different for different heads, right? We are not sharing anything across heads over here, but here we are sharing the values of the keys across the two heads. So that's how the kr matrix is computed. And the big another big difference is, of course, kr has rotary positional encoding included into it. Now we see how the queries is computed with rotary positional encoding encoded, or with rotary positional encoding injected. So if you see on the left hand side, we down projected and up projected, right? The same thing is going to happen. We are first going to down project wdq, and this is the same dimension dc dash which we saw over here, dc dash. So we are going to take my input 4 by 8 and we are going to down project it by multiplying it with wdq. So this gives me my cq matrix, which is 4 by 4. That's the same cq matrix which we saw over here, right? So similar to wkr, we have wqr now. And note the dimensions of wqr. The dimensions of wqr is dhr into nh. So this is not being shared across heads, unlike wkr. So that's why even in the description we have separate, we use additional multi-head queries which are separate for different heads and a shared key. So the key thing which DeepSeek actually implemented is that when they actually constructed these matrices with rotary positional encodings injected, the queries matrix were not shared across different heads. They were different for different heads. So this CQ was multiplied by WQR, whose dimension was DHR into NH already. So we don't need to multiply across heads in this case. So CQ you multiply with WQR and then you get 4 by 8. Why 4? Because 4 are the number of tokens over here. Then you apply rotary positional encoding and then you get your QR matrix. See, now you have the QR matrix and KR. Both have the size 4 by 8. So the dimensions of both are DHR into NH. But the way we get these is different, right? Because in the KR, we actually expand across the heads. So we share these values across heads. But in the case of the queries matrix, there are different for different heads, because the dimensions of WKR, the number of columns is equal to 8. Whereas the number of columns of WKR is equal to 4. So take a look at the dimensions which I'm using here, right? I'm using how many dimensions? I'm doing D, which is my original dimension. I'm using DC, which is my latent dimension. I'm doing DC dash, which is my queries down projected dimension. Then I have something which is called as a DHR. I have something which is called a DHR, which is my rope dimension, and I have NH, which is number of attention heads, and I have DH, which is my original head dimension. So all of these variables which you are seeing on the whiteboard right now, you will find all of these variables over here. You will see DHR, you will see NH, you will see DC dash. So I'm using the same variables so that after this lecture you can go back and completely understand what is written in the code over here. Okay, so let's see what all we have covered so far, right? So on the left hand side of the screen, we computed KC, VC, and QC. So if you see the paper now, we have KC, we have QC, we have KC, VC, and QC, which have been computed. Done. And on the right hand side of the screen, we have KR and we have QR, which have been computed. So on the right hand side of the screen, we have um, QR, which has been computed, and we have KR, which has been computed. So we have finished step number 9, step number 10, step number 11, step number 12, 13, 14, and 15. So what happens in step number 9, 10, 11, and 12? 9, 10, 11, 12, 13, that's everything on the left hand side. We first get the CKV matrix, we get the KC and the VC. That's what we started with. Remember, we first get the CKV matrix, then we get KC, and then we get VC. We saw that. Then after that, in equation number 12 and 13, we get CQ and we get QC. So down projection and up projection of queries. Here is what we see. We get down projection of queries to give me CQ, and then we get up projection of queries to give me QC. Great. So here we have exactly mapped equations 9, 10, 11, 12, and 13. Then we go to equation 14 and 15. In equation number 14, what we do is we do the QC part, right? We start with CQ and we multiply with WQR. What's being shown over here? We start with CQ and we multiply with WQR, and then we apply rotary positional encoding to it. That's how we get the uh, QR. And then in equation number 15, we multiply the input with WKR, and then we expand it across the heads. That gives me my KR. Okay. So we have covered everything until steps 9, 9, 10, 11, 12, 13, 14, 15. Now let's come to step 16, 17, and 18. What happens next is that we have KC, QC, VC, where no rotary positional encoding is applied, and we have KR and QR, right? The next step for us is to find the attention score. So let me rub this a bit so that um, the next step for us is to find the attention scores, right? So the way we do it is that we will multiply the queries multiplied with the keys transpose. And to get the queries, what I do is I have my QC matrix, which is the 4 by 8 matrix, correct? That's my QC matrix. And I have my QR matrix, which is my 4 by 8 matrix. So I'm going to concatenate these two matrices together. So I have this QC over here and I have the QR over here. I'm going to concatenate these two matrices together. So QC and QR. And similarly, I'm going to concatenate my KC matrix and my KR matrix and my KR matrix. So I'm going to concatenate KC and QC and QR to give me my full queries matrix. I'm going to concatenate KC and KR to give me my full keys matrix. And I'm going to multiply this entire queries multiplied by this entire keys transpose. And then I can split it out mathematically, right? I can split out QC multiplied by KC transpose plus QR multiplied by KR transpose. So QC, when I multiply QC and KC transpose, I'm not doing rotary positional encoding at all. So I can do the absorption trick and get my attention scores, which is a 4 by 4 value since there are 4 tokens. And when I do QR into KR transpose, it's again, so QR is 4 by 8 and KR transpose will be 8 by 4. So this will be 4 by 4. So then I have one attention scores which is 4 by 4, another attention scores which is 4 by 4. So I add these two attention scores together to get my final attention score. Then I will scale it. I will scale it by square root of DH plus DHR, where DH is my original dimension, head dimension equal to 4, and DHR is my rotary dimension, which was equal to 4. So I will scale it by divided by square root of 8 so that the queries multiplied by keys transpose variance is constrained within 1. Then I apply softmax, I get my attention weights. These attention weights will then be multiplied with VC. Remember, VC is what we already computed to be 4 by 8. So this 4 by 4 matrix will be multiplied with the 4 by 8, and then I get my context vector matrix, which is a 4 by 8 matrix. That's all. So in the schematic, or in the equations you see, we first, in this step number 16, we concatenate QC and QR. In step number 17, we concatenate KC and KR. And in step number 18, what we are doing is that we are doing multiple things here actually. We are scaling it by square root of DH plus DHR. We are applying softmax. So this step gives us the attention weights which we saw over here, the attention weights. When we scale it by square root of dh plus dhr and apply softmax, and then this multiplying with the value vector here, that gives me my context vector matrix, which they call O. The context vector matrix then ultimately goes through my output head, and that gives me my logits matrix, which they have denoted by UT over here. But what we have done on the whiteboard right now is I've visually shown you uh, just on this simple whiteboard that how we can go from step number 9 to step number 10, 11, 12, 13, 14, 15, 16, 17, 18, and 19. So this is the entire multi-head latent attention logic which was implemented in just one page in the DeepSeek paper. It's very, very, very difficult to understand this without writing it down on a whiteboard. And for me also, it took around 1.5 months to construct this lecture because it was quite hard to figure out these dimensions honestly. And some minute details like the keys are shared in the rotary part, but the queries are not shared. So to truly understand this lecture, you also need to understand rotary positional encoding, which we covered in one of the previous lectures. But through this trick of decoupling, we can use our absorption trick on the part which does not use rope, and we can treat the other part separately. Then we get the attention scores, attention weights, context vector matrix, and that's the whole flow. So if you scroll back up and see the diagram which they have given, um, this is the multi-head latent attention diagram, right? Now you can begin to appreciate this diagram a lot better. You start with the input embedding, which they are denoted as HT. Then first, let's see what we did on the uh, queries side, right? On the queries side, there are two parts. There are QC and QR, which you will ultimately concatenate. On the keys side, there is KT and there is KR and there is KC, which you will ultimately concatenate. That's what's shown with this concatenation, right? And in the query part, there is one more thing. In the query, you do the down projection. So first you get the CQ and you apply rope to CQ to get the QR part. So if you remember what we did in here is that we apply rope to CQ to get the QR. So to the down projected query. So that's what's shown in this part. We first get the down projected query, we apply rope by multiplying with WQR, and then we get QR. And then we concatenate QC and QR. On the right hand side, what's shown is that we first get the latent CKV matrix. That's how we get the KC and the VC. Right? This was what we saw in the left hand side of the board. We get the latent CKV matrix and then we get the KC and the VC. But one more thing which is shown here is that we take the original matrix and we apply rope to get the KR, and then we concatenate KR and the KC to give me my concatenated K matrix, and then we apply latent attention. So here this part, the absorption trick, the QC, the KC and QC, the QC and KC, the absorption trick works, and the other part QR and KR is treated separately. And then we get my final context vector matrix, which is denoted as U over here. So one thing you might be thinking about is what is this dash over here, right? Which says cached during inference. And it seems to imply that we only need to cache two things, the latent KV matrix and the KR matrix. So let's see in the schematic. In the schematic, I showed you that we need to cache the latent CKV matrix. This much seems fine because even in the original latent attention, we only cached the CKV matrix. And since the left side of the board is the original latent attention, it makes sense that we only cache the CKV. But in the right hand side, if you observe carefully, I have shown a black box, not these two black boxes, but I'm talking about this black box over here. I've shown black box, a dotted black box for the KR matrix, because now along with caching the CKV matrix, we also need to cache the KR matrix because we have additional computations over here. So in the next part of this lecture, we are going to see what happens exactly when a new token comes in during inference, and why do we need to cache two matrices. We need to cache the CKV matrix and we also need to cache the KR matrix. So let's see that right now. So let's say a new token comes in which is bright. So imagine that we are doing the inference and the next day is, and the token which is inferred is bright, right? So now when bright comes in as a new token, let's see how we predict the next token through this entire MLA plus rotary positional encoding framework, right? So we have to go through two paths: the attention scores path 1 and the attention scores path 2. What is path 1? Path 1 is basically no rope, and path 2 is where we are going to apply rotary positional encoding. So as we saw before, path 1 is QC into KC transpose, and path 2 is QR into KR transpose. So let's go to path number 1 right now, and let's then go to path number 2. Remember, in path number 1 we are going to use the absorption trick. So path number 1 proceeds in a very similar manner as our basic latent attention, but with the down projection and the up projection of the queries, right? So what we are going to do now is that whenever a new token comes in, we first find its input embedding, and then instead of earlier, if you see earlier, what did we have in the absorption trick? In the absorption trick, earlier we had WQ into WUK transpose, but now WQ won't be there. Instead of WQ, we have WDQ and WUQ, which are the down projection and the up projection. These will be absorbed. So in our previous implementation, this was just WQ. So now my QC, which is my absorbed query vector for bright, will be X, which is the input token only for bright. So that's 1 by 8 multiplied by WDQ, the down projection query, multiplied by WUQ, the up projection query, multiplied by WUK transpose. So again, pay careful attention to dimensions. This will be equal to D. WDQ will be my down projection. So take a look at the dimensions over here. My down projection will have DC dash, which is equal to 4, and my up projection will again transfer it into D, and my UK transpose will be take a look at the WUK dimensions. The WUK, this is my WUK transpose. So this is 8 multiplied by 4. This 4 is my latent space, which is my DC, and my 8 is equal to D. So when you multiply all this, you get the absorbed query vector for bright, which is now going to be 1 comma 4. And then what you need to do is you need to compute the latent KV vector for bright. So this is going to be the input embedding for bright 1 by 8 multiplied by WDKV, right? And that gives me the new CKV vector 1 by 4. And remember, I'm caching this. I'm caching my CKV, right? So the original CKV which was there, that was 4 by 4, and now I have an additional 1 by 4 matrix based on this new token, which will be updated to my latent KV cache. So my new KV cache will be a 5 comma 4 matrix, right? And then what I need to do is that to get these attention scores, I just need to multiply my absorbed query vector into my updated KV cache. So remember the power of the absorption trick. We are again using it over here. We only need to cache the latent KV. We don't need to cache the keys or the values separately at all. So we are going to use my absorbed query, which is 1 by 4, 1 comma 4, and we are going to multiply it with the updated KV cache transpose, which is 5 comma 4 transpose. So multiplication of this will give you an attention score for bright, which is 1 comma 5. Why are there 5? Because now I have the next day is bright, and the attention score I'm taking with bright as the query with itself and with all the other tokens. So that's why it's 1 comma 5. If you feel that I went a bit fast through this part, it's because we have already covered this in the latent attention. The only difference is that instead of WQ, we have WDQ into WUQ. So please go back and revise the latent attention lecture if this part is not very clear to you. So we calculated the attention scores through path number 1 right now, which was a 1 comma 5 vector. And here we only needed to cache the latent KV. That much is good. Now we don't stop here, right? Because we need to compute the attention scores through path number 2 as well, which is where my rotary positional encodings will be injected. So here I have to compute QR multiplied by KR transpose. The way it's done is that, remember, first we'll compute KR. So we multiply the input with WKR. So the input, which is 1 by 8, which is the token embedding for bright, is multiplied with WKR. It is 8 by 4. Remember, this is DHR, which is equal to 4, the rotary, each attention head dimension in my rotary space. So this product will be 1 by 4. I will apply the rotary positional encoding to it, which will preserve its size. So my keys vector will be 1 by 4, but this is only for one head. So I'll need to expand it across two heads so that it will be 1 comma 8. And one more thing which I want to mention here is that we are going to cache my KR matrix, right? So if you see the KR matrix which was computed earlier, this had a size of 4 comma 8 for the four tokens, and we have cached it. And now I am going to append my new KR vector to this cache. So I am going to append my 1 by 8 vector to the 4 by 8 cache, and that gives me my updated KR cache, which is a 5 by 8 matrix at the moment. Okay, so this is my KR, but I still need to compute my QR, right? So to compute QR, remember the first thing we have to do is compute CQ, which is down project the input embedding by multiplying with WDQ. That's exactly what we are going to do. We are going to take my input embedding vector for bright, which is 1 comma 8. We are going to multiply it with WDQ, which is 8 by 4. 4 is DC dash, which is the latent down projection, which we also saw over here, latent down projection in the query space. So my CQ will be 1 by 4, and I will multiply it with WQR, which is 4 by 8. That will give me my 1 by 8 vector, the query vector for the new token, and I'm going to apply rotary positional encoding to it, which gives me my QR. We don't need to cache this at all because that's the query vector for the new token, and I have my KR, updated KR cache, which is 5 comma 8. So to get the attention scores for bright in this second path, we just multiply the query vector QR 1 by 8 multiplied by updated KR cache transpose, so multiplied by 5 comma 8 transpose, so this will be 1 comma 5. That will be the attention scores for bright computed through the second pathway. So through the first pathway, the attention scores for bright is 1 comma 5. Through the second pathway, also the attention scores for bright is 1 comma 5. Then what we are going to do is we are going to add these two vectors together, and that is going to give me my resultant attention scores 1 comma 5. So if you zoom out and take a look at this entire calculation, there are only two things which we need to cache. For the attention scores path 1, we only need to cache my CKV, which has the dimension equal to DC. And in my attention space number 2, I only actually need to cache KR. And since we are actually only repeating in the KR, we are repeating across heads, I only need to cache DHR. I don't need to cache for multiple heads. I just need to cache for one head, DHR. So the total dimensions which I'm actually caching is DC plus DHR. I believe the reason they shared the values in the KR across multiple heads is so that we can reduce the computational memory. Because when we ultimately see the KV cache size, it will be dependent on DC and DHR. So actually, if different values were there across heads, the total dimensions which we will need to cache would have become DC plus NH into DHR. But now, since we are sharing it across heads, it will just become DC plus DHR. So once we only cache the CKV and the KR, we get the resultant attention scores, that's 1 comma 5. And we already have the updated KV cache 5 comma 4. We multiply it with WUV 4 comma 8. That gives us the VC, which is the values. And then we multiply the resultant attention scores with the values, and that gives me my context vector for bright, which is 1 comma 8. And for the next token prediction, I only need the context vector for my last token. So this ultimately gives me my next token prediction, right? So right now in this section, what we saw is what happens when a new token comes in. When a new token comes in, we have two pathways. First pathway, I use my absorption trick. I get the attention scores, and I only need to cache CKV. The second pathway, I get the Q, I get the KR, I cache it, I get the QR, and I multiply QR multiplied by KR transpose, and I get my attention scores for bright through the second pathway. Then what I'm going to do is that I'm going to add these two attention scores, and that gives me my resulting attention scores for bright. That's a 1 comma 5 vector. These are the resultant attention scores for bright. Then we already have the updated KV cache, right? And we have already found, and we have already have the WUV. So we multiply the KV cache with WUV to get my updated values matrix, which is 5 comma 8, and the attention scores will be multiplied with the values matrix, and that gives me a 1 by 8 vector, which is the context vector for bright. That's it. And this context vector is then used for the next token prediction task. This is the whole pipeline which is there for new inferences of tokens. And the beauty of this pipeline is that we are definitely reducing the cache size, as we'll come to later. But throughout this entire pipeline, we are not sharing information across heads, right? In the left hand side, we are not sharing any information across heads. In the right hand side, the only place where we are sharing information is here. Uh, the only place we are sharing information is KR. So that's why memory is reduced through the KV cache size, but performance is also maintained because we are not sharing too much information across heads. Now what we can do is let's come to the last part where we actually compare the KV cache size across all the variants of the attention mechanism which we have seen so far. So here's the KV cache memory size comparison. Remember, the whole thing started with reducing the KV cache memory size, but at the same time, we want to maintain the performance, right? So the original KV cache size in multi-head attention was 2 multiplied by 2 multiplied by L, B, S, and H. What are these different things? This H is my attention head dimension, N is the number of attention heads, S is the number of S is the context length, B is the batch size, L is the number of transformer layers. I'm assuming a 16-bit representation for each parameter. So we have 2 bytes over here. And the reason this one more 2 is there, it's because we have a K cache and we have a V cache. So K and V. So that's why for the original multi-head attention, it's this much memory size. What MQA and GQA tried to do is that they tried to share values across heads. So what that did is that instead of having this n in multi-query attention, we get rid of the number of attention heads completely. So that saves my memory size a lot, but that degrades my performance by a huge amount because my content is shared across different heads. So the diversity is not there in the attention scores, and my models just don't perform well on various evaluation benchmarks. Even GQA, if you see, they are better than MQA because instead of sharing values or instead of replicating values across all heads, they divide it into groups. So each group has the same value, or one group, then second group, third group, fourth group, etc. So each group has the same value, but different groups have different value. Among one group, all attention heads share the same value. It's a bit better than MQA, but still the performance is not quite good. So if you see actually, uh, in appendix D1, I think in the DeepSeek paper, they have a comparison between MQA, GQA, and multi-head attention, the DeepSeek paper. And here you will see that MQA and GQA perform much worse on all these MMLU benchmarks, CMMLU benchmark. They perform much worse than the multi-head attention. So although the KV cache size is reduced for MQA and GQA, their performance is not good at all. So ideally, we wanted something which maintains the performance and reduces KV cache size. And that's where MLA plus RoPE comes into the picture, right? The last MLA which we saw, that was the basic latent attention mechanism. What it did is we don't need to now save two values for K and V. So one, two is gone here. We only need to save the latent KV cache. Secondly, instead of saving the keys and the values, we only need to save my latent matrix, right? So instead of this N into H, we just have DL over here, which is the dimensions of my latent matrix. So this is the memory size formula for the multi-head latent attention, and we saw that this is significantly lower than the multi-head attention, but it also maintains good performance. With MLA plus RoPE, the thing which we saw today, the only thing which is modified in this formula is instead of just having the latent CKV, which we saw over here, CKV is being cached, that much is fine. But along with CKV, we are also caching DHR, right? Why we are caching DHR? Because that's KR, and we only need to cache it for one head since it's replicated across different heads. So the memory size is now DL plus DHR. And in the original DeepSeek paper, they use DL to be 4 times H, where H is the attention dimension which they have, and DHR they used H by 2, where H is the original attention head dimension. So that's DH. So DHR they used h by 2, and DL they used 4 times DH. So if you now divide MHA divided by MLA plus RoPE, you'll get that MHA is higher by a factor of 2 into NH divided by DL plus DHR, right? So that will be 2 into N into H divided by 9H by 2. So this will give you 4N by 9, and N, which is the number of attention heads which was used in DeepSeek, that is equal to 128. So in DeepSeek, if you compare multi-head attention with latent attention plus rope, you'll see that multi-head attention takes 57 times more memory requirements as compared to MLA plus rope. So latent attention plus rope actually saves the memory capacity, as is shown over here, by 57 times. So this is 9 by 2 HL. Where does this 9 by 2 come from? So DC is what we are calling DL over here. That's 4 times H or 4 times DH, and DHR is DH by 2. So overall this comes to 9 DH by 2. So what you can see over here is the capability, right? A multi-head attention has a strong performance, whereas GQA and MQA don't have good performance. Whereas MLA hours, so when they say hours, it's MLA plus rope, that has a great model performance. Plus, at the same time, they reduce the KV cache by a huge amount compared to the multi-head attention. So with MLA plus rope, we truly get the best of both worlds. We get the capability, plus at the same time we get the KV cache memory reduction. I hope all these formulae make sense to you now. Once you visually understand what is happening on the whiteboard in these computations, you will know why there is DL plus DHR here, which needs to be cached. So DeepSeek had this graph where they actually compared MHA and MLA. Forget about the MOE part for now. That's the mixture of experts. We are going to come to that later. For now, just look at the MHA and MLA part. You'll see that the MLA performance is mostly equivalent or better than the MHA, and that's amazing, right? We actually get a better performance with latent attention, while at the same time we save the cache. So here you see KV cache per token in MLA is 34.6 K, and here it's 860. So here there is a factor of 25 or 30, and here again there is a factor of 6 or 7. So we save the memory, plus at the same time you get great performance. That's the beauty of the latent attention with rotary positional encodings. And the reason I believe DeepSeek added rotary positional encodings is to get the better performance values, which we see over here in all these benchmarks. But they truly achieved the best of both worlds. They reduced the memory size and got a good performance. In this one lecture, we have covered everything which is present in the DeepSeek version 2 and version 3 paper on multi-head latent attention. I believe I have not left out anything. Now you can truly understand this entire diagram. I already explained you this diagram previously, but now you can see these. You can understand the shaded portions also. You only need to cache the KR, that too only for one head, and the latent CKV. That's why it's shown with a dash over here, and that's why it's shown cache during inference. So you will understand this schematic. You will understand all of these equations: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So this I believe until here, when you start reading the DeepSeek paper, the architecture part of it is extremely important, but it's also very difficult for people to just read through it. You need to make notes, and even when you make notes, you need to go deeper into it. I hope this lecture serves as a key facilitator for you to understand everything in the DeepSeek paper. Just like I have done with latent attention, my next target is going to be a mixture of experts. So the mixture of experts is one of another incredible innovations in the DeepSeek paper. We are going to go through that, and after that, we are going to go through multi-token prediction. Thanks a lot, everyone. And this was one foundational lecture in building and understanding DeepSeek from scratch. It took a very long time for me to prepare this lecture, but I hope it was worth it. And I hope all of you have really understood how latent attention plus rotary positional encoding was implemented by DeepSeek. Thanks a lot, everyone, and I look forward to seeing you in the next lecture.